So we saw the demonstration of our two wires. So I'm going to have a wire with the current going that direction. I've got a wire with the current going this direction. So this is going to have current I1. This will have current I2. We know that our magnetic field is equal to and that's where mu is equal to 4 pi times 10 to the minus 7. So we have that. We're going to separate these by a distance d. We're going to do a point. I'm going to do 3 different points. This is going to be a point that's 2d away. That's our d. So this is going to be 1/2 d. And this is going to be 1/2 d. And this is going to be a point d away. This is going to be point A. This is point B. This is point C. If I do my right-hand rule, we're going to be able to figure out the direction of that current. So for I, it's going to be into the page. So that for current 1, it's going to be into the page that way. And it's going to be out of the page for I1. Now, if I'm doing this one for 2, it's into the page here, and 2, it's into the page. It's just further away, right? I'm doing my right-hand rule, and I'm in kind of a nice contortion here. Now, but for this side, it's going to be out of the page for 2, but it will be into the page for 1. So we've got which way we've got it going. I can add the magnetic fields. So the total magnetic field total is going to equal the magnetic field from 1 plus the magnetic field from 2. I don't have to worry about my direction because we're accounting for direction based on my right-hand rule. So for at A, our magnetic field net, which is equal to the total magnetic field, is going to equal, for the current, I'm going to have, well, mu over 4 pi, or 2 pi, sorry, mu over 2 pi is going to be for both of them. So I can break that one out. And then I'm going to have current 1. Now I'm at A. Current 1, we're going to call out of the paper positive, into the paper negative. And so current 1 is 2d away. Current 2, I'm going to be into the paper. And we are 3d away. So that's going to end up being, so I'm going to end up getting mu 2 pi 1 over d current 1 divided by 2 minus current 2 divided by 3. And that would be the net magnetic field at point A due to those 2 wires. Okay, let's do B. So at B, our net current is going to equal, I can pull out my 2 pi. I have my current 1. But at B, it's going into the page. So I'm going to have to put a negative. And I'm at D over 2. For the second one, I've got I2 over D over 2. And it's also into the page. So that's why it's got its negative. So I have that lovely. So now we're going to get mu 2 pi 1 over D. And I have minus 2I1 minus 2I2, which I can simplify again. I'm going to take out my minus 2 mu over 2 pi I1 plus I2. And I got a D in there. Almost left my D off. So now I get a minus mu pi over D, sum of the currents. So we'll do the last one we'll do for C. It B net equals so if I'm going over here, I got the minus I1. Now C is 2D away, so I'm going to have 2D. And now I2 is positive because we went and we looked at it that way. So I get my I2 is positive and it's only D away. So now if I simplify this, I get mu 2 pi D I2 minus I1 over 2. Hopefully that all makes sense. And just for grins and giggles, just like we've seen before, if this is my wire, and I'm looking at the distance away, this is going to be the decay of my magnetic field. And it'll be modeled by 1 over R. And just for grins and giggles, just so that we have it in the notes and we have it on here, this is a Tesla meter amp. Just so we've got units to play with.